P. They make up what I'll call life's formula, HOCNP. All organisms, great and small, engage in a relentless search for these elemental ingredients, gathering them from the environment to build their bodies. Those that succeed, survive. Those that don't. When evolution produces an organism that can gather these elements in a novel, more efficient, and more successful way, it sets the stage for that organism to change the world. How can the evolution of a single type of organism change the entire world? The answer lies in life's formula. In one configuration, these elements are the building blocks of all living matter. In another, they combine to make the gases in the air that keep Earth warm for life to persist, say phosphorus, whose very different role I'll devote a whole chapter to later on. Thus, if evolution produces an organism that can pull unprecedented amounts of one or more of these elements from the environment, the concentration of heat-trapping gases in the air will change, and thus the climate. The more outsized success an organism has in gathering the ingredients of life, the more dramatic climate change will become. In this way, these elements link life and climate, in the past, present, and future. The three world-changing organisms in this story sit on very different branches of the tree of life: microbial, plant, and animal. In Part 1, we'll dive deep into the geologic past to tell the story of the first two world changers, cyanobacteria and land plants. We'll explore how the single-celled cyanobacteria evolved new ways to gather the constituents of life's formula, particularly carbon and nitrogen, and precipitated the biggest environmental change of all time, the Great Oxidation Event. Then, we'll fast-forward almost 2 billion years and introduce the second world-changing class of organisms, land plants. Their evolutionary innovations in gathering hydrogen, oxygen, and phosphorus allowed them to spread across the previously barren continents. But plants' proliferation inexorably sent the then-tropical planet, with bathtub-temperature oceans at the North Pole, into an ice age that froze many of the world's first forests out of existence. In both cases, we can understand these changes through the elements in life's formula, which connect us all to the planet we inhabit. The history of cyanobacteria and land plants also sets the stage for the story of humans, the third great world changer. In Part 2, we'll focus on how human industry, innovation, and proliferation has precipitated a new geologic era called the Anthropocene. Despite all the obvious differences between us and our plant and bacterial predecessors, we are linked by a common elemental thread, HOCNP. Indeed, this link is the key to unraveling the complex web of global environmental woes wrought by modern society. Understanding that is the key to Part 3, where we'll look to the future. Like our predecessors, our remarkable access to these 5 elements has brought enormous benefits while pushing us inadvertently toward environmental catastrophe. Mitigating the unintended consequences of our remarkable innovation depends on our management of the elements we are using to change the world. If we want a more sustainable future, we have a lot to learn from those who came before us. Now that I've briefly introduced our 3 organisms, let's take a look at the 5 atoms that make up life's formula and shape our climate. The approximate formula for a cyanobacteria cell is 263 hydrogen atoms, 110 oxygen atoms, 106 carbon atoms, 16 nitrogen atoms, and 1 phosphorus atom. The approximate formula for a human cell is 375 hydrogen atoms, 132 oxygen atoms, 88 carbon atoms, 6 nitrogen atoms, 1 calcium atom, and 1 phosphorus atom. Indeed, I could write a formula for any living creature, and it would be very similar to these. Of the more than 100 known elements, these 5, plus or minus calcium for those with bones or shells, are the most abundant in every organism on Earth. In the same order of abundance,